Hello, and welcome to Physics for Play. In this episode, we're going to continue our discussion of the simple harmonic oscillator. We're going to show how to solve the differential equation for the simple harmonic oscillator by making a guess, plugging it into the equation, and then showing it provides the correct solution. Let's get started. Let's actually figure out how we can solve this differential equation. A differential equation is just like an algebraic equation, except instead of solving for x, where you're using algebra, it's going to be an equation that also has derivatives in it. So you're solving for some function x rather than some variable x. So we are going to do a few different things. We're going to look at our differential equation. In general, and I had a calculus professor tell me this, really the only way to solve a differential equation is to either know what the right answer is or to just guess and check that it's the right answer. So we're going to do some guessing and checking, and then I'll show you what Mathematica does to make it even easier, which is a command called dsolve. So let's start with our differential equation. I've actually typed it out ahead of time to get us started quickly. But looking at our equations, we've got Newton's second law, force is mass times acceleration. But acceleration is the second derivative, x double prime, as a function of time. So I can say force is mass times acceleration, which is equal to mass times x double prime here. Again, notice that I'm putting in the double equal sign here, not the equal sign, which is for assigning values to things. That'll be important. So if you're coming up with errors in your code, make sure you check that. But the forces, the spring force is also given by Hooke's law, which is minus the constant, the spring constant times the position x. And here we're going to write x as a function of time. So we are going to solve that differential equation, and we're going to solve it by guessing and checking. So we are, let's take a gander at what a good solution might be. When we're guessing, if you want to sound sophisticated, if you want to be like one of the cool kids, you are going to use, you're not going to say you're guessing, you're going to use a word called ansatz, which is basically a fancy German word for guess. So we're going to make an ansatz because that sounds fancier and more appropriate. So we're going to guess what the function is. So I'm going to put a comment in here, and this is going to be my first guess. It's guess number one. And since this is a harmonic oscillator and it's going boing, boing, boingy, it's going up and down, I am going to guess that that solution is going to be some sine or cosine function. So I'm going to define a function. So I'm going to define x of t, which I write this way with the square brackets. And I'm going to put an underscore after the t because it might work without it, but I've always done it with it, and I think that's how you just write things in Mathematica. I think that's how you define functions. So I'm going to write x of t, and I'm going to give it, I'll give it a constant a in front, and then I'll make it a sine function. And then I'm going to put in a few constants here. I'm cheating a little bit because I know what the solution is. And we'll see what each of these constants actually means momentarily. But this is going to be my guess. Then what I'm going to do is I'm going to just take the other equation I've typed in. So here I'm defining what x of t is. And then I'm just going to have it plug into x double prime of t, or mass times x double prime of t is minus kx. Just plug it into my differential equation and see if that gives me the correct solution. So I do that. I see something that maybe kind of looks right. Sorry, I forgot to do one thing. I mentioned this in the first episode of Physics with Play, but if ever something looks wonky, you got to make sure you quit your kernel. In this case, you'll notice there's no spring constants in my equation. There's no k's in there. The reason you do not see a k is because earlier when I was making the plots, I defined k equal to 1. So now it is in there, it's just showing up as 1. So it's not actually going to make an appearance here. So I'm going I'm going to quit my kernel, quit that one time. You'll see once I evaluate this, the K and the M are going to be blue, so it means it's undefined again. Since I want to do this for general K, I want to be able to plug K in later, so I want to be able to track where it is. So now you can see my K is back in there. And you can see this kind of looks like it's what we want. Maybe it's got a sine phi plus t omega. Not really sure if that's the right equation. So let's simplify that a bit. We're going to use a command called simplify. And I can do one of two things. I could just Control C and copy that and paste it in here. Or Mathematica has this nice feature where you take a percent sign. The percent sign just means put in the last thing that you outputted. So it'll put in this whole equation. So we're just going to simplify the previous result. And you can see it just kind of moves our variables around, makes it a little nicer to look at. And when it does this, you can kind of see what we need to happen in order for this equation to make sense. Because you can see you've got this sine function. Now that sine function has a time in it, has that t in there, which stands for time. And that if this equation is going to be true at any time, I've got to have the rest of this equation be equal to 0, because this thing's going to be changing. Again, the sine function goes up and down and boingy, boingy, boingy. So that's going to be constantly changing. So that's not going to be the thing that's equal to 0 for this to hold. I need this something over here to be 0. Well, if I set a equal to 0, and a, it turns out, is the amplitude of this sine function, well, then I have no amplitude and it's not going boingy, boingy, boingy. So it can't be that's 0. So it's got to be this thing that's 0. So what this tells us is that this equation works provided I take this omega, so this is the Greek letter omega, not a W, provided that omega is such that this part of the equation is equal to 0, because then this whole side will be 0 and then the solution works. So it's got to be true that K equals M, and then we can make our omega symbol using escape, W escape, which gives us the omega. It's got to be true that K equals M omega squared. And if that's the case, then this solution works great. So we're gonna get to plotting and animating this result in just a minute, but I want to show you a few other versions of this because it turns out this is not the only solution that works. All the solutions I'm about to show you are entirely equivalent, but they're shaped a little bit differently because they use different trig functions. So we're going to define this, and then this equation is going to look very similar. I'm just going to replace the sine with a cosine. So it'll be cosine omega t plus, and I'm going to use a different phase shift because sines and cosines look like exactly the same thing. The only thing that's different is the sine function is phase shifted by 90 degrees. So I'll do that. I'm actually, just to keep things neat, I'm going to comment out the first equation. The second equation will overwrite the first one, so you don't need to do this, but I like to, commenting it out gives it that kind of faded out green color, and it's just easier to follow. So we'll just run the same equation again. This time everything's the same. You run this equation, everything's the same, except you got a cosine argument. You get a cosine in the answer. As before, you get the k minus omega squared, so k has got to be equal to m omega squared for this to be true. I'm going to do one more version of this, which you also see in common use. Again, x of t colon equals. This time, this is going to look a little bit different. I'm going to say it's equal to c1 cosine omega t plus c2 sine, sine omega t. So you might say, isn't this just the sum of the two? Well, it's not quite the sum of the two. First of all, the constants are different. Second of all, you'll notice we got rid of the phase shift. So inside the sine function is not omega t plus phi naught. It's just omega t. And here inside the cosine function, it's not omega t plus phi 1 or phi 1. It's just omega t. What you will find with differential equations like we have here, this is known as a second order differential equation, and that means being second order means I have two constants that you need to determine with your initial conditions. So in the case of the first function, the sine function, it was the constants were what were the amplitude and what was the phase. Same thing for the cosine function. For the sum of the sine and the cosine function, it's just the two different coefficients on the sine and the cosine. This is looks a little bit more complicated, but again, we can run through this. We can simplify. Again, we've got that k minus m omega squared factor that shows up, which tells us that the k, the spring constant, has to be equal to m omega squared. So as long as I pick the frequency at which that sine and cosine oscillates correctly, it'll be, if we solve for it, it'll be square root k over m. Everything will be hunky-dory and that solution will work. That is all for this time. Join us again next time, where we'll be showing how to plot the results from that differential equation we just solved. Like the video if you liked it. If you'd like to see more, please click the subscribe button, and we'll see you next time.